Today I'm going to be presenting MendelFuzz. This is one of the mutation-based fuzzing papers. It was published in 2025 at FSE, Foundations of Software Engineering Conference. And it was created by some researchers from the EPFL University at Switzerland and the Max Planck Institute from Germany, so this is a Euro paper. So we're going to start with just a quick overview of fuzzing, which you're probably aware of, but I think it's always useful to cover the basics. So fuzzing is an automated technique for finding bugs. It does this through the core fuzzing loop of we take a seed from our seed pool, which was some previous input, we mutate it, and then execute it. After execution, we check if it, one, crashed, so did it crash, which indicates we found a new bug, which is good, or if it didn't crash, we then analyze its trace and we filter it out. And we're filtering out for interesting execution. So did we find new coverage? Did we hit a new edge? So if we have an interesting case, we then add that to the seed pool, and we can kind of just continue this process forever or for a defined period of time with the goal of trying to find unique crashes. With modern fuzzes, we generally start with a corpus of valid seeds. So this is a set of known valid inputs to populate the seed pool before starting your process. The benefit of doing this is that you then have seeds which you know are valid behavior, because you always have the problem that if you give invalid input to a program, you're then not necessarily fuzzing the actual main body of the program, but just the input-output setup, where a lot of the times you don't really care about the passing ability of a program, you care about its actual functionality, because in the real world, people don't just give like an invalid MP3, you're giving it a valid data. So then if we also look at this process, we kind of see that the main crucial part of a fuzzer is a mixture between its mutator and filter, and in this case we're focusing on the mutation part of it for this paper. A fuzz's effectiveness depends on its starting seed pool, its ability to generate valid, interesting mutants, and its filter. And this paper covers the first 2 points of that. So we can see that the mutation part of a fuzzer is important. So next we're going to look at the mutation strategies fuzzers use, and in particular what MendelFuzz looks at. So there are a lot of mutation philosophies, but the core challenge is essentially how do you generate mutants that are both valid and interesting. As we just previously mentioned, an invalid input kind of tests the passing point, the passer of a program, but you're then not testing the actual internals of the program. But at the same time, if your test isn't interesting, if it doesn't actually find crashes or doing different behavior, it's not useful. So going back to kind of how the fuzzers work, you start with your original code, which usually starts off as valid code, and then you make a series of changes to it. If your changes make it no longer a valid input, so let's say you're fuzzing a compiler, if you give it non-valid code, you're then not going to actually get the compiler to do its core behavior. So ideally you want to change the input in such a way that you are breaking the internal functionality of the program, not just the passer point. And in general, making a small change means that your mutant is more likely to be correct, but less likely to find new behavior. So this is kind of where you have this core challenge trade-off with the mutator, where larger changes mean you get to interesting behavior quicker, but at the same time you get to invalid behavior quicker. So in a simple fuzzing loop, mutation only occurs inside the loop. So in this diagram, the mutator only exists at one point, but in reality there's actually two stages to fuzzing with modern fuzzers, where we have this deterministic stage and the havoc stage. This deterministic stage is new in the sense that in 2013, AFL introduced a deterministic stage. This occurs in between the seed corpus and seed pool. The idea is that you take your seed corpus of valid inputs and then you apply a lot of small changes to them to actually increase the size of your seed pool. So then out of these two stages of deterministic and havoc, MendelFuzz looks into the deterministic stage. So of the two stages, the deterministic stage takes your original seed corpus, and for every byte in that seed, it applies a small known change. So we systematically apply single mutations to each byte of a seed, and then for each byte change, you generate a new mutant. These are things like bit flips, adding, subtracting, value replacement, a bunch of small changes. The idea is going back to the original idea of kind of a small change means that a mutant is more likely to be valid, and you want valid inputs. And since there's such a large number of inputs, this takes a huge amount of time in terms of generating the mutants, but then also just processing all of them. The advantage is that we generate a bunch of inputs that are extremely likely to be valid. Downside is it's very expensive and most of them are non-interesting. You then have the other idea of the havoc stage, which is kind of your more traditional mutator, where you do a large number of random changes. It's likely that there's a higher chance of making the code invalid and breaking it, but at the same time, there's a higher chance of finding interesting behavior and finding a bug. So you kind of have this paradox of choosing between the two cases. And then we also get to what this paper in particular is looking at is that the deterministic stage was dropped due to this kind of paradox, where the deterministic stage found the majority of edges, so on average 62%, but it would take over 90% of execution time. So this was really expensive. What this paper FuzzBench found was that they just disabled the deterministic stage, and they found that for actually a lot of test cases, it was more time efficient and cost efficient to just disable that and go straight to the havoc stage, and that it would find that even though if you spend 96% of the time in the deterministic stage, you get 62% of the edges, if you just gave all of that time to the havoc stage, it found most of them. So this led to a lot of modern fuzzes disabling it, like AFL++. So we get to then this core problem. What this paper looks at is that the deterministic stage was dropped because it was so expensive. But if you actually look into the deterministic stage, you kind of find that 0.5% of the bytes accounted for 84% of the coverage gains, and 20% of the seeds accounted for the 83%. So this means that the majority of your time spent in the deterministic stage is wasted, which is why papers dropped it for the havoc stage only. But there is if you could get out the sort of core gold part of the deterministic stage, then it is worth doing, but only if you can get around that huge cost of it. And this is where MendelFuzz comes in. It tries to bring back the deterministic stage by only going for the core parts which got the useful values. So MendelFuzz dives into the deterministic stage, and they actually split the deterministic stage into two parts: the deterministic fuzz map and the critical bytes identification. And each of these stages sort of tackle the two sort of core findings they found, which is that 20% of seeds result in 83% of coverage. So if you can find these 20% of seeds, or at least the subset of seeds which get you more coverage and can ignore the rest, you can speed up and have a more efficient deterministic stage. And also their second finding of, well, only 0.1% of bytes being toggled or changed, mutated, results in 84% of coverage. So if we can find that subset of bytes which produces interesting behavior and ignore the rest, we can, again, speed up the deterministic stage. And if you can do these two aspects at the same time, you're able to get a huge performance increase without losing sort of the benefits of the deterministic stage. So let's first look at the deterministic fuzz map. The idea here is that we want to select the subset of seeds which actually find a lot of the coverage. So we want to get the subset of seeds which get that sort of 80% of coverage we found originally. The idea of how this paper tackles this is that they say if there are two seeds which are very similar, we only need one seed. So if you have two identical copies, why do you need two copies? You only need one. In this case, they define two seeds as two tests which get the same coverage, or more accurately, a test which doesn't find new edges, you don't keep. So the way this process works is you take a seed from your corpus, you run it, and get a coverage map, extract its coverage map, and for any new behavior this coverage map find, you'd add that to your global coverage map. If it found new coverage, you then actually add that to the deterministic seed pool. Otherwise, you just pass it on to the normal seed pool. And that way you only take a subset of the seeds. The next stage is the critical byte identification one. So going again, even if a seed can find interesting behavior, only 0.5% of the bytes are going to lead to new coverage. So you want to quickly identify which bytes are worth mutating and going through the process. And ideally then find the ones which are not interesting. So the way they do this is they start by doing some havoc-based mutation, where you change a bunch of stuff until you find some new coverage or new behavior. Once you then find it, you then do a binary search and find the subset of bytes which need to be toggled to get to that new behavior. And by doing that, you can then isolate which bytes are leading to the interesting behavior. Once you then have a subset of bytes which lead to interesting behavior through this havoc testing, you then know, okay, we're going to keep these bytes, we're going to put these bytes through the ring and do all the different mutations. And after doing all those, and then we can ignore the rest of the bytes. So we're able to then go from maybe doing 100 bytes to only looking at 10%. It doesn't ever get to that 0.5% of interesting bytes, but again, we're just dramatically decreasing the search area. Ultimately, this leads to pruning 80% of the seeds and 95% of the bytes, which allows MendelFuzz to achieve deep code penetration without that huge time penalty. So next we're going to just look at some of the experimental results the paper found. So in this slide, they compared MendelFuzz to kind of the state-of-the-art fuzzes at that time, so like AFL, AFL++, with a few different settings. And you can see that MendelFuzz was able to, on the left with their normalized coverage, it could get sort of between 96 to 98% of coverage on a bunch of different tests, where for that same given period of time, the other fuzzes which weren't using the deterministic stage were sitting between 86 to 90%. And then again with fuzzing, because they kept the deterministic stage, they found more bugs where these bugs were sort of found in either from the deterministic stage that they had, or because of the seeds that the deterministic stage set them up for to find. So overall, they were getting better results in the same time period. Then here was kind of interesting case of where they were able to, by decreasing the amount of time they spent on the havoc on the deterministic stage, they were finding more bugs in havoc. But you can also see here that now instead of 90% of the time being devoted to the deterministic stage, now 90% of the time is given to the havoc stage. And that for a lot of cases, for some of these tests, they don't get some interesting behavior from the deterministic stage. Particularly, you can see that middle one, the ASNL PASA. But in the other cases, by spending between like 1 to 2 to maybe a max of 10% of time in the deterministic stage, you're getting at least 30% or more coverage from the deterministic stage. Which just kind of shows that you can get huge benefits by implementing this. So then what were the effects and results from all of this? What impact did this paper have? Well, kind of the biggest effect and sort of the proudest effect MendelFuzz sort of has their badge of honor is that AFL, after AFL originally created the deterministic stage, later then decided to drop it for its efficient trade-off. AFL++ has now actually re-added the deterministic stage, the deterministic strategy with the MendelFuzz implementation, and has now set that as the default strategy. which that's kind of their badge of honor, what they're particularly proud of. But I think future work kind of shows that, one, it's important to, sometimes you might have a good idea but haven't implemented it correctly, and sometimes you need to revisit it, which I think is kind of interesting what this paper shows. This paper, I think, also just shows that there's a lot of benefits and sort of progress to be made on the deterministic stage, so kind of the pre-fuzzing core fuzz loop, that there's still optimizations to be made there. And that I think also in particular this critical byte detection can be useful in the havoc stage, where instead of maybe using the havoc to do general mutations and mutating a bunch of bytes at once, I think if you're able to then identify specific bytes which are leading to more coverage and more errors, to have your mutator focus primarily on those bytes while still focusing on other areas could also maybe be an area of future research and could lead to interesting behavior. Thank you for listening to my presentation.